Hello everyone, welcome to College Algebra Lecture 6. And this lecture is on section 2.7 from the textbook, which is on linear inequalities and absolute value inequalities. So basically we'll be solving inequalities equations, but instead of involving equals sign, they will involve greater than, less than, greater than or equal to, or less than or equal to. Okay, but before we do that, we have to review how to write what's called interval notation, because in MyOpenMath, a lot of the answers you have to put in interval notation when you're representing inequalities. So let's talk about that first. So using interval notation. All right, so to motivate this, let's look at an example. Let's say we want to show this inequality x is less than or equal to 3. And I want to show it using 3 different methods. I want to show it using something called set builder notation. Then I want to show it using interval notation. So I'll describe what that is, interval notation. And I also want to illustrate it using a graph. So how would we graph this inequality on a real number line? Okay, so let me start off with set builder notation. So a set is represented by like a pair of curly brackets. So if I do, say, an opening curly bracket, x, actually, and then I'll explain what all these little symbols mean. The vertical line, and then the inequality itself, x is less than or equal to 3, and then close curly bracket. So the way you interpret this is the opening curly bracket and the close means the set, right? So this is the set. You can think of the x as meaning of all x. The vertical bar here you can read as such that. And then the rest of it after the vertical bar, this is the condition, right? So this would be the inequality part. So the set of all x such that, and then x satisfies that condition, the fact that it's less than or equal to 3 in this case. Okay, so that's set builder notation. We won't use it too much, but I wanted to mention that. Interval notation is very important. We're going to use this throughout the semester. So interval notation. I would write, so I'm doing exactly the same thing, the same example, x is less than or equal to 3. So that means x is going to start way down at negative infinity, right? Because that's less than negative. That's less than or equal to positive 3. So I would start at negative infinity. So I'm including all my x's here, all the way to 3. And then I want to include 3, so I'm going to use what's called a square bracket. So let me explain this. So parentheses means don't include the endpoint. And you always use parentheses whenever you have negative infinity or infinity, because they're not really numbers, right? They're just telling you that the it's growing either without bound, either getting very, very, very large, or very, very, very small, right? It's not an actual number itself. So always, I'll say always use parentheses with negative infinity or positive infinity. Okay. The square bracket means to include the endpoint. So I want to include the 3 in my set. So square bracket means include the endpoint. Okay, so that's interval notation. So that's basically saying all x from negative infinity all the way to 3, including 3. Okay, that's the same thing as x is less than or equal to positive 3. Now, for a graph, so now I have the real number line. Of course, it goes on forever, right? I'm just going to do to positive 5. And then to the left is negative. Okay, so I want all the x's that are less than or equal to positive 3. So basically, everything from 3 to the left is included, right? So everything from 3 to the left is included. Let's see if I can make this darker. So usually you write or draw an arrow to represent it keeps going. And we're also going to include 3, and the way you denote that is you put a filled in circle there. So a filled in circle on a graph means include the endpoint, and an open circle means don't include the endpoint. Okay, so that graph represents x is less than or equal to positive 3. All right. Let's do another example. Let's say I have the inequality x is greater than negative 4. So I want to write it in set builder notation, interval notation, and then draw a graph. Okay, so set builder notation is simply going to be the set, right, of all x such that, remember the vertical line means such that, and then the condition is simply the same thing, x is greater than negative 4, and then I close the set with the closing curly bracket. In interval notation, well, I want all x greater than negative 4. So like negative 4, negative 3, negative 1, 0, 1, 2, 3, 4, all the way to infinity, right? Would satisfy that. So I start at negative 4, and I'm not including it, right? How do I know that? Because I don't have an equals there, right? It's strictly greater than. There's no equals, right? Just greater than. So I would start at negative 4. Since I'm not including it, it's got to be parentheses, comma, and I'm going all the way to infinity. And remember, with infinity or negative infinity, we always use parentheses. So that would be the interval notation. And then for a graph, so I don't want to include negative 4, so that's going to be open circle, and I want everything to the right. So everything in that direction would be included. So that would be the graph of x is greater than negative 4. Okay, what about this? What if I have x is, this is sort of like a compound inequality. X is greater than or equal to 2 and less than 5. So that's how you read that. X is greater than or equal to 2 and x is also less than 5, right? So it's everything in between. So for set bundle notation, it's basically the set of all x such that, and I can just write that same inequality down again, greater than or equal to 2, less than 5. For interval notation, well, I'm starting at 2. I want all values between 2 and 5. I don't want to include 5, but I do want to include 2, right? Because it's greater than or equal to, x is greater than or equal to 2. So how do I denote that? I have a square bracket at the 2, and I don't want to include the 5 because I have strictly less than 5. So how do I denote that? That would be parentheses. So open square bracket 2 comma 5 close parentheses. That is the correct answer. And then for the graph, I don't really have to do negatives here, but I'll do a couple of them. Okay, so I want 2 to 5. So 2, but I'm including 2, so that, remember, that's a filled-in circle. I'm going to go to 5, and then don't include 5, so that would be open circle. So all the x's in there would be part of that solution. Okay, and there's an infinite number of them, right? Everything from 2, including 2, all the way up to 5, but not including 5. What if my oops, let me go back to black. How would I represent all real numbers? Well, you could just state it, right? You could say, like in set bundle notation, I could say it's the set of all x such that x is a real number. And that's enough to tell me, right, it's all real numbers. Or I could write like this. I could say it's a set of all x such that x is greater than negative infinity and less than infinity. Okay, and again, we don't ever use equals there because infinity is not a real number, right? It just says it's growing without bound, either very, very large or very, very small. How would I write that in interval notation? Well, I would start at negative infinity. Again, I have to use parentheses for infinities, comma, and go all the way to positive infinity. And then in terms of a graph, basically what we would do is just go in both you'd have an arrow going to the right, arrow going to the left. So it includes all the real numbers, right? That would be the graph of the set of all real numbers, or x is greater than negative infinity and less than positive infinity. Okay, what if I want to exclude a single value? So let's say I want to use interval notation to express all real numbers except, say, negative 2. Okay, so really what that means is I want to write all the numbers where x is less than negative 2, right, but not including it, or, and that or is going to be important, x is greater than negative 2. So the way I can do that, well, x is less than negative 2. I can write that in interval notation by starting at negative infinity. Remember, I have to use the parentheses, comma, and I want to go all the way to negative 2. I don't want to include it, so that's parentheses. The or, we use what's called a union symbol. So it's like a large U for union. And then I want to start at negative 2, but again, not including negative 2, comma, and go all the way to positive infinity. So that means all real numbers except x equals negative 2. So this is a union symbol, and it means it's the same thing as saying or. Okay, so now that we have that notation down, and again, the most important notation is going to be the interval notation. So let's talk about solving linear inequalities in one variable. So to solve linear inequalities in one variable, what you want to do is you want to solve it as if it's an equation. So let's say solve it as if it's an equation. But there's one exception. The one exception is if you multiply or divide both sides of the inequality by a negative value. So the one exception is if you multiply or divide both sides of the inequality by a negative value, then you must reverse the inequality, reverse the sense of the inequality. In other words, a greater than becomes less than, a less than becomes greater than. So you must reverse the inequality. Okay, so if at any time when you're solving the inequality, if you ever multiply or divide, and usually it's at the end when you divide, if you ever multiply or divide by a negative value, then you have to just switch the sense of the inequality. All right, so here, let's do an example. Let's say this is my inequality. And I want to solve it. Okay, so I'm going to solve this as if I'm solving a regular equation. Treat the inequality, so in this case the less than, as like an equal sign to start. So what do I need to do first? Well, normally I would get rid of that positive 3, right? So I need to subtract 3 from the left-hand side because I want to isolate the negative 2x. Whatever you do to one side, to the other side. Subtract 3. Have I multiplied or divided by a negative? No, I just subtracted a number. That's fine. So this is still less than, and negative 3 minus 3 is negative 6. Okay, now, how do I get x by itself, 1x? Well, I would have to divide by negative 2, right, at this step. Whatever I do to one side, do to the other side. But here's that exception. Because I divided by a negative value, that less than now becomes a greater than. And then negative 6 divided by negative 2 is a positive 3. Okay, so let me just highlight that. So I divided by negative 2, so I have to reverse the inequality. Right, so less than became greater than. That's why I did not stop. And then how would I write my answer in interval notation? Well, it would be x is greater than 3, so it's all x's, right? The solution is going to be all x's greater than 3, but not including 3, so it'll be parentheses 3, comma, and I'm going to go all the way to what? Infinity, right? Because it can be, and then obviously I have to use parentheses for that. So that would be my answer in interval notation. Okay. Here's another example. Okay, so again, treat the inequality symbol as sort of like an equals, right? Solve this as if it's an equation. You only have to worry about that one exception. If you ever, at any step, and usually it's at the end, if you ever multiply or divide by a negative value, you have to switch the sense of inequality. So what would I normally do first? Well, I'd have to distribute to 2, right? Multiplying that 2. So that would be 30x minus 18 plus 7 is less than 17 plus 11x. Okay, then what would I normally do? I would combine like terms, right? So negative 18 plus 7 is negative 11. Then I would try to get the x's on one side of the equation. So let me bring the x's to the left-hand side. So I'll subtract 11x. So that's going to be 19 x. And I'm going to get rid of the 11, so I'll add 11 to both sides. So 19x is less than, what's that, 28? And then finally, I would divide by 19, right, by a positive 19. So at no point did I ever multiply or divide by a negative value, so I'm still fine here. So this is still going to be less than, and in 28 19ths, I can't really do much, so I'll just leave it as 28 19ths. So then in interval notation, this would be negative infinity, comma, all the way up to 28 19ths. And since it's strictly less than, I don't include that, so that'd be parentheses. Okay, you could also have what's called a compound inequality. So let's do one example like that. Let's say I want to solve the compound inequality. It basically has like two parts, right? So what this says is that I have negative 5x minus 6. It's greater than or equal to negative 26, and it's less than negative 11. But I can write that all in one as one large inequality. And you can also solve it as one large inequality. So normally what would I do to isolate the negative 5x? I'd have to get rid of that negative 6, or I have to add 6. So as long as I add it to every side here, then this will work. So negative 26 plus 6 is negative 20, less than or equal to negative 5x, less than, and then negative 11 plus 6 is negative 5. And now what would I do to get x, 1x? I would have to divide by -5. So then -20 divided by -5 is 4. -5 divided by -5, -5x divided by -5 is x. And then -5 divided by -5 is 1. But because I divided by negative, I have to flip the sense of all those inequalities. So the less than or equal to becomes greater than or equal to, and then this becomes greater than. Okay? Now, it's written kind of a funny way, right? Because now it's saying 4 is greater than or equal to x, which is greater than 1. But we normally don't read it that way. You write the lower number first. But we can just flip this around, and this is equivalent to saying x is greater than 1 and less than or equal to 4. Right? These mean the same. These are exactly the same. How would I write that in interval notation? Well, I'd write it as parentheses 1, comma 4, but then I also want to include the 4. So that would be my answer in interval notation. Now, if you don't like solving a compound inequality that way, you could always do it the following way. So let me go back to that same example. Let's say I have -26 is less than or equal to -5x minus 6 is less than -11. You could split this up, right? You could say I have the fact that -5x minus 6 is greater than or equal to -26, and -5x minus 6 is less than -11. So it's like two, right? I can solve those two inequalities and then put them together at the end. So to solve this, I would add 6. We're going to get the same answer, but let me just walk through this. So I have -5x greater than or equal to -20. Now I need to divide by -5. So this is x is less than or equal to 4. And in this side, I have +6 plus 6. So -5x is less than -5. Divide by -5. And I get x. Since I divide by negative, I have to flip that, right? So it's greater than 1. So how do I write both x is less than or equal to 4 and x is greater than 1? Well, if I put those together, right, I get exactly what I had before. X is greater than 1 and less than or equal to 4. Or in interval notation, 1 comma 4 square bracket. Okay, so you can do it separately and then put it back together at the end. Think of what this is looks like graphically too, right? If x is less than or equal to 4, that's going to be everything. Well, it's going to include 4, and it's going to be everything to the left. And then if x is greater than 1, it's not going to include 1, and it's everything to the right. And if both of those are true at the same time, it's going to be exactly what's in between, right? So it'll be not include the 1, include everything else, including the 4. And that's what we're finding. Okay, next, and actually this is the last topic of this section, is solving absolute value inequalities. Remember last time we solved absolute value equations. Now we want to talk about absolute value inequalities. Okay, so solving absolute value inequalities. So an absolute value inequality has the form either absolute value of some expression is less than some expression, or it could be absolute value of some expression is less than or equal to some expression, or it could be absolute value of some expression is greater than another expression, or it could be absolute value of some expression is greater than or equal to another expression. Okay, and remember, if you have absolute value of some number, I'll call it, say, like little a or something, it's defined to be the distance from 0 to a. So is the distance from 0 to a. Okay, so I think this idea of distance is maybe the easiest way to explain this. So let's say we have an inequality. So if you have an inequality say absolute value of x is less than k, where x is some expression, then this means all values x whose distance from 0 are less than k. So this means all values x whose distance from 0 are less than k. Right? Because the absolute value part, the left-hand side, absolute value of x, means the distance from 0. And we're saying the distance from 0 has to be less than k. If we draw in a picture, right, if this is 0 on the real number line, let's say this is k, and this is negative k. Well, if the distance has to be less than k, I can't include k or negative k. Let me do it in red. So I can't include k or negative in k, but everything here, both on the positive side and negative side, has a distance that's less than k. Right? If the value is, say, right here, well, that distance is less than k. If it's here, the distance is less than k. Anywhere in here, the distance is going to be less than k. So this can be written basically as a compound inequality, as x is greater than negative k and less than k. Right? That's what it means. Now, if you want to include the endpoint, right? Let's say if you have absolute value of x is less than or equal to k, then it's almost the same thing. This you would rewrite as x is greater than or equal to negative k, less than or equal to positive k. The only difference is now you're actually allowing the endpoint to also be included in the solution. Okay? So in this case, it's saying that this distance is less than or equal to k. So in this picture over here, you would include the endpoints. Right? Any of those values would make sense. Now, if we go the other way, right, let's say greater than. So if I do absolute value of some expression is greater than k, it means all values x whose distance from 0 are greater than k. In terms of a picture or a graph, right, if this is k and this is negative k, well, all the distances greater than k are going to be things either, but remember, we're not including k, so that's open circle, but anything over here, all the way to positive infinity, right, that distance from 0 will be greater than k. Or anything less than negative in k, but again, not including it, because so anything to that side, all the way to negative infinity, would also have a distance greater than k. Okay, and then the way that you write that, so say this can be written as x is less than negative k, or x is greater than positive k, right? So I have two pieces in this case. X is less than, that expression is less than negative k, or that expression is greater than k. And then if I include the endpoint, it's almost the same thing. So if I have absolute value of x is greater than or equal to k, this is similar, and it can be written as, it's basically the same thing, except now I would have x is less than or equal to negative k, or x is greater than or equal to k. All right, so let's try some of these. And I think this is the easiest way to solve these types of problems. There are other ways. You can do it graphically. You can set the absolute value equal to 0 first and then go from there. But I think this is the easiest way to actually do like a systematic approach of doing these problems. So here's an example. Let's say I want to solve absolute value of x minus 7. So there's my expression, right? That's like my big X, is less than or equal to 7. Well, remember, I can write this as, if you want, think of this as, right, the big X. Remember, I could write this as the big X was greater than or equal to negative 7, less than or equal to positive 7. So in this case, I would say little x minus 7, that's like my big X, is greater than or equal to negative 7, less than or equal to positive 7. And now let's solve it. Well, it's a compound inequality. I can solve it all at once if I want. So I can do this by adding 7, right? Because I want to get the x by itself. I add 7, I add 7. So this is going to be, I guess, 0, less than or equal to x, less than or equal to 14. And then if I want to write this in interval notation, my answer would be, since I'm including 0, it's square bracket, 0, comma, 14. I'm also including 14, so close square bracket. Any x in there, including the two endpoints, will solve this initial problem, right? So like if x were 3 or pi or 7/2, right? Those are all values in the interval. It's going to make that true. Solving it means it makes it true, makes the inequality true. Okay, do a few more examples and then that'll be it for this section. So let's say I want to solve this absolute value inequality. Absolute value of 2x minus 8 is greater than or equal to 1. So again, right, this is like my k. So remember, one possibility, sorry, not my k, it's my x, like my capital X, right? I called it capital X. This is like my x. So one possibility is that x is less than or equal to -1, or x is greater than or equal to +1. The 1 is like my k. Right, so capital X, that whole expression, is less than or equal to -1, or x is greater than or equal to +1. All right, so knowing that, I can write out those two possibilities. I can say the capital X, which is my 2x minus 1, one possibility is it's less than or equal to -1, or 2x minus 8 is greater than or equal to +1. Let me solve both of these. So I'll add 8. So I have 2x is less than or equal to 7. Divide by 2. So one answer is x is less than or equal to 7 halves. Or, and in this one, I'll add 8. I get 2x is greater than or equal to 9. Divide by 2. So x is greater than or equal to 9 halves. Okay, how do I write this in interval notation? Well, x is less than or equal to 7 halves. So that's going to be, I'll start at -infinity, and I go all the way to 7 halves, and I include it, right? So square bracket. The or, remember, is the union, right? And then x is greater than or equal to 9 halves. I start at 9 halves, including it. So square bracket, comma, and I go all the way to +infinity. Remember, the infinities always have a parentheses. Okay, here, let's do one more. So let's say I want to solve 5 times absolute value of x plus 1 plus 4 is greater than 12. Well, first thing, I need to isolate the absolute value term. I'm just going to write this over again. Right, you want to isolate the absolute value term. So I would subtract 4, right? Get rid of that 4 first. So I have 5 times absolute value of x plus 1 is greater than 8. And then I'd have to divide by 5, right? Divide by 5. So I have absolute value of x plus 1 is greater than 8/5. So remember, that means, right, there's two possibilities. Either that expression is less than a -8/5, right, less than -k, or that expression is greater than +8/5. It's the only way the distance can be greater than 8/5. So in this case, I would subtract 1. Well, what is subtracting 1? It's the same as, so this is like -8/5 minus, you can think of 1 as 5/5, right? So you have the same denominator, lowest common denominator, which is 5. And what's -8/5 minus 5/5? That's going to be -13/5. Or, and here if I subtract 1, I get x is greater than, well, this is going to be 8/5 minus 5/5. So that's x is greater than 3/5. Okay, so let me put these together in interval notation. So x is less than -13/5. That means I start at -infinity. I go all the way to -13/5. but I don't include it, right? So parentheses, or, so union, x is greater than 3/5, so don't include it, 3/5, go all the way to infinity, and then parentheses again. So that would be my solution written in interval notation. Any x in that interval is going to be a solution to that original inequality. All right, great. So that's it for that section. And actually, we're done with chapter 2. So the next lecture we'll start on chapter 3, which is functions.